This is section 8.5 about drawing Lewis structures. Now, there are 5 different things that we follow. I would like you to read them and then step into the next slide. So the first one we're going to do is the hydronium ion. What we're going to do is we're going to see how many electrons are on hydrogen. It's an S1 and there are 3. We're going to see how many valence electrons there are on oxygen. Here's oxygen, it's an S2P4 and there are 6. When we add 3 plus 6, we get the value 9. Now the hydronium ion has a positive charge. That means we have to remove an electron, so we have 8 electrons that we need to distribute. I already drew my skeleton, and what I'm going to do is I'm going to put 2 electrons in between the central atom and the terminal atoms, and when I look at this, I have used 2, 4, 6 electrons. What I have left are 2 electrons left over. I'm going to place them around the oxygen, and now if you look, you can see that we have 8 electrons around the oxygen. Our octet is complete. I realize I put all the words in, so I'm going to ask you to pause, read the words, and verify what I just did. When we do the hydronium ion, what we would have for an acceptable Lewis structure is replace each of those shared pairs of electrons with a single line. We would put a bracket around the skeleton structure, and we would put a plus to show that it's the hydronium ion. Now, I've recorded this a number of times, and if I go through it slowly, my video is too long to be accepted by YouTube, so I've had to make some changes. Here we have an anion, the arsenate anion. Arsenic, right below nitrogen, S2P5, 5 valence electrons. Oxygen, S2P4, 6 valence electrons. 3 oxygens, 3 times 6. And since it is an anion, we have to add those 3 electrons to take into account the negative charge. That gives us a grand total of 26 electrons. Now, a question students will ask is, how do I know what the central atom is? Well, the atom that is written first is the central atom, and that is arsenic. And what I'm going to do is I'm going to put 2 electrons between the arsenic central atom and the oxygen terminal atom. We started with 26 electrons. We've just used 6 electrons. We have 20 electrons left. I'm going to place those around the terminal atoms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 13, 14, 15, 16, 17, 18. Oh, I know this is like grade school counting, isn't it? What I have are 2 electrons left over. You're going to run into this a lot as you draw structures, and what you do is you place them on that central atom. Now, you're not supposed to draw a little circle around it, but I usually do to designate that it is a lone pair. So an acceptable Lewis structure of arsenic, it would have those shared pairs replaced by the single line. And then one needs to put these little electrons around all the terminal atoms. That is the rule. Since we have an anion, we would put a bracket around it and we would place a -3. So again, I've talked through it. The words are here. Pause this video and absorb what has been said. Here's our third example. It is formaldehyde, that is embalming fluid. So carbon, S2P2, 4 valence electrons. Hydrogen, S1, 1 valence electron. There are 2 hydrogens. Oxygen, S2P4, there are 6 valence electrons. All in all, we have a total of 12 electrons. Once again, I've put carbon in the center, and I'm going to put my 2 electrons surrounding that central atom. I had 12, I'm using 6, I have 6 electrons left over. Hydrogen only requires 2, so it is done. So what I need to do is put those 2 electrons around the oxygen, the 6. 1, 2, 3, 4, 5, 6. Now, oxygen has a gorgeous octet, but carbon, it only has 6 electrons. So what we're going to have to do is rearrange them. And the way we do that is we take a pair of the electrons on the oxygen, and we put it between the carbon and the oxygen. Now you'll notice that each carbon and oxygen does have an octet, and the correct Lewis structure would look like this. It would have a single bond for one lone pair shared. It will have a double bond for two pairs shared. No need to put a bracket. This is a standalone molecule. Again, an example. My last example is carbon monoxide. Carbon, 4 valence electrons, S2P2. Oxygen, 6 valence electrons, S2P4, for a grand total of 10 electrons. Well, I'm going to put those 2 electrons in between. I'll subtract them. I have 8 electrons left over. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, things do not look very good. I only have 4 electrons around oxygen while I have a nice octet around carbon. And what you're going to have to do as you learn to do this is you just have to try things. Rearrange the electrons until each atom has an octet. Kind of wish I left more room here, but essentially I will have those 3 pairs of electrons in between the carbon and the oxygen. Now each of them has an octet. So you may think, oh, it's fine to just put in that triple bond, but please remember you also need to show the other electrons for a valid Lewis structure. So that's part 1 of this section. The other part has to do with a concept called formal charge. It is not real like an oxidation number. What it does is if you have more than one Lewis structure, it helps you determine what's the most reasonable Lewis structure. And you're going to use this when you take organic chemistry a lot. You will say the most stable structure has the smallest formal charge on each atom, and the most negative charge will be on the most electronegative atom. So I'm going to just give you, so we can explain this, the Lewis structure for the cyanide ion. Here it sits. You can take some time and determine it, but there it is. And there's a process that we follow. We say, all right, we have a C, we have an N. We have valence electrons, all right? So carbon has 4, nitrogen has 5. And what then we have to determine is which electrons are assigned to each of the atoms. And if I look at carbon, what I'm going to do is I'm going to put a little dime down the center, and I'm going to say each bond has to be split in half. So I have 1, 2, 3, 4, 5. I have 5 electrons that are assigned to carbon. We only have half that come from the bond. So when I would subtract that, I would come up with a -1 charge. Okay, that's the electrons assigned to each atom. And that's the formal charge. We always subtract the number assigned to each atom. Now, take a moment and look at nitrogen, and what do you see? Well, 1, 2, 3, 4, 5. I would subtract 5 from nitrogen, and I would get a 0. So that's how we determine a formal charge. It's usually in a very large molecule, and normally you write the formal charge somewhere near the element. And you'll see that when you take organic chemistry. We don't do it quite so much in Gen Chem. We just teach what formal charge is. Well, that's where you received the structure for the material. Let's do the same thing now with carbon dioxide. I'm going to just draw the 2 valid Lewis structures for carbon dioxide. You'll notice one of them has 2 double bonds to give every atom an octet. You'll notice another valid Lewis structure has a single bond and a triple bond. All right, so we're going to do the exact same thing. We're going to have a line that says, what are our valence electrons? Well, oxygen has 6, carbon has 4, oxygen has 6. So that's an easy part. Now, what are the electrons that are assigned to the atom? Remember, we count the electrons directly on the atom, And then we take 1/2 of the electrons in the bond. So oxygen has 1, 2, 3, 4, 5, 6. We subtract 6, we get a 0. Carbon, it has 1, 2, 3, 4. We get a 0. The other oxygen is symmetric to the first one, and we get 3 zeros as the formal charge. Let's see how it changes for the other valid Lewis structure. When I look at my oxygen on the left, I count 7 electrons, giving this a -1. Carbon still has 4 electrons, giving this a 0. And oxygen has 5, giving this a +1. Well, what we want to do is we want the one with the lowest formal charges. And there's a lot of debate about all of this. But what happened is people went in and did an experiment. And they showed that carbon dioxide is nonpolar. It had a 0 dipole moment. And that implied that it was symmetrical. And that also implied that the formal charges are all 0 on all of the atoms. So this would be the more acceptable Lewis structure. Again, there's going to have to be practice in order to really get a hang on this. But these are your 2 examples. Please use them. The first one was to say, how do I assign a charge? The second one was to say, I have 2 Lewis structures. Which of these 2 is going to be the more acceptable? And I've recorded this a number of times, so I'm going to leave it at that.